Think about the last time you installed an app on your Mac. You probably clicked download, dragged the icon to your applications folder, and opened it without a second thought. Behind the scenes, the operating system is constantly checking the digital signature of that app, verifying that it comes from a trusted developer and hasn't been tampered with. This is the certificate validation chain, the backbone of trust in the macOS ecosystem. But what happens when that trust is weaponized against the very people who built the system? This is the story of the recent security incident involving OpenAI and the Axios library, a case study that exposes how deeply a supply chain attack can penetrate the core of application security. When we talk about supply chain attacks, we often think of hackers stealing credentials or injecting code into popular repositories, but the incident in question reveals something more insidious. It highlights a critical vulnerability in the continuous integration and deployment signing pipelines. A compromised third-party dependency, specifically the Axios library, managed to bypass standard code review processes. It injected malicious code directly into the build artifacts. This wasn't just a simple script running in the background. It was a payload designed to interact with the macOS certificate validation chain itself. Here is the thing that makes this attack so dangerous. The malicious payload did not try to break the encryption. It tried to convince the system that it was legitimate. By exploiting a specific cross-app resource access vulnerability on macOS, the attackers created a pathway for the compromised build tools to interact with signing keys and other sensitive system resources. It forced an emergency certificate revocation because the trust anchor itself had been compromised. This suggests a potential decoupling between build infrastructure integrity and end-user data protection in modern AI application architectures. Even if the user data remained secure, the integrity of the application itself was put into question. Now consider the technical mechanics of how this payload interacted with the validation chain. In a standard scenario, an app presents a certificate signed by a recognized authority. The operating system verifies the chain of trust from the app back to the root certificate. In this incident, the payload manipulated the environment in which that verification happened. It exploited the way macOS handles cross-app resource access, allowing the malicious code to intercept or alter the validation process. It is similar to a forger not just copying a driver's license, but somehow convincing the police officer that the fake license is real because the lighting in the room was just right. The system saw what it was programmed to see, but the context was corrupted. This event accelerates the industry shift towards zero-trust build environments. The reliance on unverified third-party packages for critical signing operations proved to be a single point of catastrophic failure. It underscores the increasing sophistication of state-sponsored groups targeting open-source libraries as a low-effort, high-impact strategy. The rapid attribution of the attack to North Korean actors highlights how supply chain vulnerabilities are no longer just a technical problem, but a geopolitical one. They are targeting the tools developers use to build secure applications, turning the development process itself into the attack vector. So, how do we defend against this? The answer lies in implementing runtime integrity checks within machine learning pipelines and build environments. We cannot rely solely on the initial signature check at installation time. We need to verify the integrity of the application while it is running. This means checking the code against known good hashes at regular intervals, ensuring that no unauthorized changes have been made to the binary or the execution environment. It is like having a security guard who doesn't just check your ID at the door, but also monitors your behavior throughout the building to ensure you haven't switched identities. To implement this, you need to move beyond static analysis. Static analysis looks at the code before it runs. Runtime checks look at the code while it is executing. In the context of an ML pipeline, this means monitoring the environment for any unauthorized access to signing keys or sensitive resources. If a build tool tries to access a signing key it should not touch, the system should flag it immediately. This isolation mechanism prevents compromised build tools from interacting with the signing keys or other sensitive system resources, effectively breaking the attack chain before it can complete. The incident also highlights the importance of decoupling build infrastructure from end-user data protection. OpenAI confirmed that user data remained secure, which is a crucial distinction. It shows that a breach in the build pipeline does not automatically mean a breach in the data storage. However, it does mean the application itself is compromised. This separation is vital for modern AI application architectures. If the build pipeline is compromised, the application can be altered without affecting the data stored in the back end. This means the application could be sending data to a malicious server while appearing legitimate to the user. The industry is now moving towards stricter dependency verification standards. Every package in your dependency tree must be verified, not just the top-level package. This is a shift from trusting the repository to trusting the verification process. It requires a more rigorous approach to signing and verification. You need to verify the provenance of every single component. This is where the concept of a zero-trust build environment comes in. You do not trust any component by default. You verify every interaction. This approach requires a fundamental change in how we think about security. It is not enough to secure the perimeter. You must secure the interior. You must assume that a component might be compromised and design the system to detect and mitigate that compromise. This is the only way to defend against the increasing sophistication of state-sponsored groups targeting open-source libraries. They are looking for the path of least resistance. They are looking for the unverified third-party package. They are looking for the single point of failure. By implementing runtime integrity checks, we can detect these compromises in real time. We can stop the malicious payload before it can interact with the certificate validation chain. We can ensure that the application is running the code it was intended to run. This is not just a technical upgrade. It is a strategic shift in how we build and deploy software. It is about recognizing that trust is fragile and must be continuously verified. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.